last time we were talking about factoring polynomials, and we actually did two problems where we were given some polynomials and we wanted to find the remainder of the polynomial when we divide it by x minus c, and then we wanted to determine if x minus c was a factor of this polynomial. And then what we wanted to do was to use the division algorithm to factor a polynomial function. So we did two problems, and I want to do two more. So here I have f of x is 2x cubed plus 5x squared minus 5x plus 28. I want to determine if x minus 4 and x plus 7 factor this polynomial, are factors of this polynomial. Okay, so remember what we do is we think of this as x minus c, and we take the c and we plug it into the function. If we get 0, then there's no remainder, and it is a factor of the polynomial. So in this case, for x minus 4, c is equal to 4. And in this case, we get x minus a negative 7, so c is negative 7. So let's plug both of these into this function. So f of 4 is 2 times 4 cubed plus 5 times 4 squared minus 59 times 4 plus 28. We're going to need a calculator for this, so let's pull one out. So let's start with 4 times 4 times 4 times 2. That's 128. Of course, you can put all of this in a calculator, but I'm going to do it piecewise. This is 80. Then 59 times 4 is 236. Okay. I'm going to add up the positive numbers and see if I get 236. So 128 plus 80 plus 28 is 236. So this is equal to 236 minus 236, which is 0. So we have no remainder when we divide by x minus 4. So x minus 4 is a factor of f of x. Now let's try x plus 7. So I'm going to plug in negative 7 into this polynomial. So I'm going to write it out first. Okay, and now I'm going to break it into little pieces. So let's multiply. This is negative 686. This is 245. For 13, 28. And again, let's add up these positive numbers and see if we get 686. So 245 plus 413 plus 28, that is 686. So it looks like both of these factor the polynomial. Okay, so x plus 7 is a factor of f of x. So let's put a little star here and a star here. So both of these are factors, which means we can write this function as x minus 4 times something and x plus 7 times something. In fact, notice that this degree is 3. Which tells me that there are 3 potential zeros or 3 potential factors of this polynomial. And it turns out that 2 of them are x minus 4 and x plus 7. So what we're going to do, I'm going to choose one of them. It doesn't matter which one. I'm going to go with x minus 4 because I think that one's going to be a little bit easier to work with than the 7. And I'm going to divide the polynomial by x minus 4. Okay, so let's make some space right here. Don't want erase all of that. Okay, so what we're going to do is we're going to put x minus 4 here, and then 2x cubed plus 5x squared minus 59x plus 28. And let's do some long division. Okay, so we ask ourselves, what do we need to multiply x by to get 2x cubed? Well, that would be 2x squared. So we distribute this, we get 2x cubed minus 8x squared. Now we're going to subtract the whole thing, which means we need to change all the signs. Okay, and so this should always become 0. This will be 8, 13 x squared, and pull down the 59. Okay, and now we ask ourselves, what do we need to add to this to make this piece? When we multiply this by this, we get 13x squared plus something. So to get this 13x squared, we need to multiply by 13x. So we get 13x squared, and then minus, that looks like 52x. Okay, so we're going to subtract this. Okay, and then this becomes 0. Notice that this is a negative 59 and this is a positive 52. So this becomes a negative 7x. Pull down the 28. And then negative 7, we need to multiply that x by this negative 7 to get that. So we get negative 7x. And this becomes a positive 28. Now we subtract this, so we change all the signs. And then you notice that we get 0, which is our remainder. Okay, so let's summarize what we found. We see that 2x cubed plus 5x squared minus 59x plus 28 over x minus 4 is equal to 2x squared plus 13x minus 7. Now we're going to multiply both sides by x minus 4. So we get 2x cubed plus 5x squared minus 59x plus 28 is equal to this 2x squared plus 13x minus 7 times this x minus 4. All right, so we have factored this partially. Notice that we have something here that is a quadratic. And to completely factor this polynomial, we need to factor this piece as well. Now what we can do is we can try to factor it our normal way. But remember that we did find out that x plus 7 is a factor of this polynomial function, which means that because these two are equal, it's also a factor of this side, which means it divides this piece here. And we can double check that if we want. We can make this a new function. We can call this g of x. So this is 2x squared plus 13x minus 7. Or if you want to stick with the division algorithm, you can call it q of x. So maybe we should call it that, because that was the quotient here. If you plug in 7, negative 7, right? Negative 7. Then this should be 0. It's going to factor it. So let's divide this polynomial by x plus 7. Just make some space here. One more time. Okay. So we're going to take 2x squared plus 13x minus 7 and divide it by x plus 7. So we'll get 2x. This becomes 2x squared plus 14x. Subtract everything. This becomes a negative x minus 7, and you see that this would be negative 1. If we multiply by negative 1, we get negative x minus 7. Switch all the signs, we get 0 for the remainder. So this factors into 2x minus 1 times x plus 7. So if that's true, then we can substitute this piece right here with this. So let's erase this and write 2x minus 1 times x plus 7. Now we have something that is completely factored. You can see we have linear factors, which means that the degree on each one of these x's is 1. And we're done. This is the complete factored form of this polynomial function. Okay, let's scroll down. All right, I wanted to do one more, particularly here because we have all the other examples we saw. When we had a degree, we also had all of the other terms, like we had for this one, this is a 4, we had an x cubed term, an x squared term, an x term, and a constant. Here I've gotten rid of some of those. I want to just show you what you have to do with this particular type of function, where you're missing some of the terms that go with the other numbers for the powers. So again, here I have a function. Let's figure out if these are factors of this function. What we're going to do is we're just going to plug in -1 and 1 into the function and see if we get 0. So what is f of -1 and f of 1? So plugging in -1, we get -1 to the 4th minus 2 times -1 plus 1. And plugging 1 in, we see that we get this is 1 plus 2 plus 1, which is 4. And the one on the bottom is 1 minus 2 plus 1, which is 0. So this one is not a factor, which goes with this one. And this one, we can see that the remainder is 0, which tells us that this is a factor. I'm going to put over here, not a factor. Okay, so we saw before that we could use the division algorithm to break the function into a polynomial times this factor plus a remainder. What we really want to do is factor things. So because I've done a couple problems involving that, where we divided this polynomial function by the non-factor and we got a remainder, and then we wrote it as a product plus the remainder. I'm not going to do that again. What I want to focus on is the factor. Okay. So what we're going to do is we're going to take x to the 4th minus 2x plus 1. Now don't write this down yet. I'm going to show you something. And I'm going to put x minus 1 here, because that's what we're trying to do. We're going to see how this factors into this polynomial. So we're going to divide this polynomial by x minus 1. Again, we should get no remainder. What I want you to do is, instead of writing this, I want you to expand it a little bit. I want to have all of the terms. I want the x cubed term, the x squared term, and if there was other things missing, I would want those terms as well. So what I'm going to do, and what you should do, is put plus 0x cubed plus 0x squared minus 2x plus 1. So I've written it in an expanded form. And this is going to be helpful when we need to divide. Okay, so now let's start the division. So x into x to the 4th, we need to multiply by x cubed. So we get x to the 4th minus x cubed. And now let's subtract this, change all the signs, and pull that x cubed down, because we get 1 plus 0 is 1. Now we pull this 0x squared down. And then to get x cubed, we need to multiply this by x squared. So we get x cubed minus x squared. Subtract everything. So now this becomes x squared minus 2x, pulling this down. Then this is plus x. So we get x squared minus x. Now subtract. This becomes a negative x, and then we pull down the 1. And then all we need to do now to get this negative x is multiply by a negative 1. So we get negative x plus 1, and then we subtract everything. And you can see we get 0, which is our remainder. So now we can write that x to the 4th minus 2x plus 1 divided by x minus 1 is this. So let's put that over here. X to the 4th minus 2x plus 1 divided by x minus 1. is equal to x cubed plus x squared plus x minus 1. Now multiply both sides by x minus 1, and we get x to the fourth minus 2x plus 1 is x minus 1 times x cubed plus x squared plus x. Let me erase that. Minus 1. Okay, so we've gotten into almost completely factored form. Notice that I got rid of one factor here, but now I have something that I could probably factor further because I have an x cubed, so maybe we can break it into some linear powers where we just have x minus something and x plus something or so on. So we're going to have to figure out something that divides this. Okay, what goes into this? Oh, let me just make sure I didn't make any mistakes. Sorry, I think I did everything okay. Let's FOIL it out just to make sure that I didn't make a mistake. So I got x to the 4th plus x squared plus x cubed plus x squared minus x. I'm just sending this back in because I want to see if it simplifies to this. Then minus x cubed minus x squared minus x plus 1. So this goes away, this goes away, this goes away. No, that becomes negative 2x. Okay, x to the 4th minus 2x plus 1. So I did factor it correctly. Sometimes, especially if you get something wrong on your homework, you might have made a mistake over here. Like you forgot to distribute the negative. So that becomes a little bit of an issue. You need to double check your work. Looks like I did everything okay. So the next piece would be, can we factor this? What happens, so I'm looking at this. Now, I'm going to tell you that you can, I don't know if we can factor this at this point. Let's see if we can plug in some other numbers in here. Like if I plug in negative 1, that won't work. So if I plug in 1, that won't work. So at this moment, we haven't learned what we need to do next, unless I give you a potential factor. So can we factor this further? The answer is maybe, possibly, we could find potential factors for this. So the idea is this is definitely factorable over the complex numbers. We might have some complex roots. We might have some rational roots, and we might have some irrational roots. So we're going to learn what we need to do to factor something like this. And in other words, where I don't give you potential factors. All of these problems that we've done, I've given you potential factors, and you found that one of them was a factor, and then we could divide. But the thing is, what if I don't give you any factors whatsoever, and I ask you to factor this? Well, it's going to be similar. You're going to come up with some potential factors, and I'm going to teach you how to find these potential factors. And then from there, we will try to factor it. And later, if we have something that's not factorable over the real numbers, we're going to have to learn how to factor over the complex. So right now, I think this is as far as we can get at this moment, because right here we don't know how to factor this. So what we're going to do is we're going to learn how to factor this, how to find some potential factors for this. So let's move on. So how can we factor a polynomial if potential factors aren't given? Okay, so I'm going to give you some strategies. And first, I'm going to tell you a fact. A polynomial function cannot have more real zeros than the degree of the function. Okay, so if we have a polynomial function that has degree 3, the most number of real zeros is going to be 3. It could have less than 3 real zeros, but the most it can be is 3. So you would have 3 factors. Like if we try to divide, we could probably find 3 potential factors. Let me rephrase that. We can find a lot of potential factors. I'm going to show you how to do that. But the most of those factors that would actually be a factor would be 3. Okay. The next thing is I'm going to give you something called the rational zeros theorem. This is going to tell you how to determine some factors. So let's say you have a polynomial function that looks like this. F of x is equal to a sub n x to the power n plus a sub n minus 1 x to the power n minus 1, and so on, just like polynomial functions we've learned. So this is your function here. The rational zeros will take the form plus or minus p over q, where p is a factor of a sub 0 and q is a factor of a sub n. So what we're going to do is when we have a polynomial function, we're going to take this number here and we're going to take this number here. And I'm going to figure out all the factors of this number. So anything that divides that number. And I'm going to find all the factors of this number. So anything that divides that number. And I'm going to take the ones that divide this number and divide it by the ones that divide this number. And that will give us a bunch of numbers that could be potential factors of our polynomial function. Now, not all of them will be factors. We could have up to n of them being factors of them, depending on what n is. That's our degree. So if we had a degree 3, if we get like 10 numbers using this formula, then a maximum of 3 of them will be a factor. And I'm going to show you some examples in just a second. Okay. And for this to work, a sub 0 can't be equal to 0, and a sub n can't be equal to 0 either. And all the AIs have to belong to the integers. So anything here, any of these coefficients have to be integers for this theorem to work, which is what we're going to look at. All of them are going to be integers. And this number here can't be 0. If it's 0, then we're not working with the degree being n. And we don't want this number to be 0 either. But if it happens to be 0, I'm going to show you an example of that, of what you're going to do. Okay, so if we look at the last problem we saw up here, where we came into a problem with this one. How we're going to find the potential zeros is we're going to look at this last number and this number in the front, which is a 1. And we're going to think of all the numbers that divide 1. So the numbers that divide -1 is just 1 and -1. And don't even worry about the sign. And the numbers that divide this number is 1. And then I'm going to put plus or minus. And so the potential rational zeros are 1 and -1, because we can have +1 or -1. And if you plug them into here, you'll get 1 plus 1. Let's say we're plugging in the +1. 1, 1, 1. That's 3 minus 1, which is 2. So this would not be a 0 of the function. If we plug in -1, we'll get -1 plus 1 minus 1 minus 1, which is going to be -2. So this one is not a 0 either. turns out that, so I'm only giving you rational zeros. I'm giving you rational candidates for this polynomial function. This one doesn't have rational factors, any more rational factors. And because of that, you're going to have to either look at complex factors or real factors, things like square root of 2 and pi. Those could possibly be factors of this. We're going to look at some examples where we're going to get rational zeros, and then we'll come back to something like this later. Okay. Now, this is a lot to absorb, so let's just do a few problems. For the following functions, let's determine the maximum number of real roots. Then we want to determine the potential rational factors, and then we want to factor. And I started off with something really easy. We've done this problem in the last video, I think 2 or 3 times. We have f of x is x squared minus 8x plus 15. All right, we know how to factor this. This is x minus 3 times x minus 5. So we already know the factors of this. 3 and 5 are the zeros of this function. X minus 3 and x minus 5 are the factors. So let's say we didn't know how to factor this. What we're going to do is first we're going to say, oh, the degree is 2, which tells us we can have a max of 2 real roots. And you can see that we have 2 real roots. We know that. Now, if we didn't have 2 real roots, complex roots always come in pairs. We'll talk more about that later. But we would either have 0 real roots or 2 real roots. Okay, determine the potential rational factors. What we're going to do for that is we're going to take this number here, 15. I'm going to put it right here. And I'm going to put a division sign. And I'm going to take the coefficient here, which is 1. I'm going to take factors of both of these numbers. So what are the factors of 15? 1 divides 15, 3 divides 15, 5 divides 15, and 15 divides 15. I'm going to put a plus minus here. And what are the factors of 1? The only number that divides 1 is 1. Okay, so now let's see how many potential factors we have. We've got plus or minus 1 over 1, which is just 1, plus or minus 3 over 1, plus or minus 5 over 1, and plus and minus 15. Just dividing each one of these by 1. So I have 1, 2, 3, 4, 5, 6, 7, 8, 8 potential factors. I'm going to write them in an expanded, let me put 0 here. I'm going to write them in an expanded form this one time, just so you can see that I have 8 of them. This 1, negative 1. 3, negative 3. 5, negative 5. 15, and negative 15. Now, if you knew nothing about this, this function here, this polynomial function, and you didn't know how to factor it, what you would do is you would take, start maybe with any one you want to start with, but you would plug one of these numbers into your function. And if you got 0, then it would be a factor. X minus that number would be a factor. Now, looking at this and looking at this, we already know that the correct ones are 3 and 5. So what I'm going to do, if I plugged in 3, which we did this in the last video, if you plug in 3, you'll get 0. And if you plug in 5, you'll get 0. So x minus 3 and x minus 5 are factors of f of x. Again, if you didn't know which ones to choose, you had no idea how it really factored, you would just start plugging them in. So if you plugged in this one and you didn't get 0, then you would maybe go to this one and plug it in. You didn't get 0, and then you plug this one into the function and you got 0, which told us because there's a maximum of 2 real roots, we found one of them. If we divide this using the long division, we would find the other root. Okay, let's move on to this one. Okay, 2x squared plus x minus 6. This is something we can factor. Let's see what it is. Negative 6, we want two numbers to multiply to give us, not negative 6, negative 12. Remember how we factor this. We take this number and multiply it with this number, which is negative 12. And then we take the number in the middle, which is 1, and we put it up here. And we think of two numbers that multiply to give us negative 12. Add to give us 1. Well, in order to get a negative, one has to be negative, one has to be positive. 4 and 3 work. They multiply to give us negative 12. They add to give us 1. So what we do when the coefficient here is not a 1 is we break this into 2x squared. We get rid of this x and write it as negative 3x plus 4x. And then you group them and you factor out what you can, which I can take out an x here. And I can take a 2 out of here. And then I can factor out a 2x minus 3 on both. Now I've gone over this type of factoring before, so I'm going through this really quickly. I just want to let you know that we already know how to factor this. But what I'm trying to get out of this is I'm trying to figure out what the potential factors are using this rational zeros theorem. I'm showing you something that you've seen before so you can understand how we find the rational zeros. Now again, if I knew nothing about this function, I see that the degree is 2, which tells me there's at least, there's a maximum of 2 real zeros. What are the real zeros here? If I set both of these equal to 0, I get x is 3 over 2 and x is negative 2. Using the rational zeros theorem, my potential factors, or my potential zeros, are plus minus factors of this number, just take the positive of it, 6, over this number, which is 2. Now let's break this. I know right now you probably think, let's just simplify this to 3. That's not what you want to do. The factors will be factors of 6, which are 1, 2, 3, and 6. Factors of 2, which are 2 and 1. I'm going to put a plus minus in the front. So all my potential zeros are the following: plus or minus 1 over 2, plus or minus 1 over 1, which is just 1, plus or minus 2 over 2, which is 1, so I don't need to write it again, plus or minus 2 over 1, which is 2, plus or minus 3 over 2, plus or minus 3, because 3 over 1, then plus or minus 6 over 2, which is 3, I've already written it, and then plus or minus 6. I'm taking all the different ways, you can see what I'm doing here, all the different combinations I can find here. And I've got 2, 4, 6, 8, 10, 12. I've got 12 potential candidates for zeros of this function. And what are the correct ones? Well, we already know what the correct ones are. They're 3/2 and negative 2. Let's look in these potential zeros. I have 3/2 written right here. That was one of the options. And then the other one was negative 2, which is written right here. So if I had no idea, I would just plug in some of these until I got that when I plug it into the function, I got 0. And the only two that will work are negative 2 and 3/2. Okay, let's look at an example where we have no idea what to do, which is this one. This is the first problem. So I have f of x is 3x to the 4th plus 6x cubed minus 15x squared minus 30x. When I look at this, notice that I don't have a constant term. When I don't have a constant term, that means that I have a greatest common factor. First off, the degree is 4. which tells me I have four potential, I could have a maximum of 4 real roots. Okay. I also notice, because I don't have a constant term, again, constant term means a number without an x, I have a greatest common factor. Let's factor out the greatest common factor. So f of x is equal to, all of these have a 3 in common, so let's take it out. And also we have an x in common. So we'll get x cubed plus 2x squared minus 5x minus 15. Sorry, I didn't divide this one by 3, so that's a 10. Okay, so here I've already found one of the roots. You see that I factored out an x, so x minus 0 is a factor, which tells me that 0 is a root of this function. In other words, if I set this function equal to 0, then 0 would be a root. So we found one of them. Now let's focus on this polynomial. What are the roots of this polynomial? So let's say x cubed plus 2x squared minus 5x minus 10. This is a polynomial that doesn't have a problem with the constant term. You see that the constant term is there. So now we can use the potential zeros theorem. So the potential zeros theorem says our potential zeros take the form plus or minus factors of -10. Don't worry about the negative because we have this plus minus on the outside, so just say 10 over factors of the number in the front here, which is a 1. So that would mean we have plus or minus 1, 2, 5, and 10. Those are the numbers that divide 10 over 1. So the options are plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10, dividing each one by 1. If we have more numbers here, then it's going to get more complicated. But since we only have one number, we're only going to get what we see up here because this number is 1. So these are all the potential zeros. Now again, we want to factor this here. Okay, originally we wanted to factor this function. We took out a 3x, so that's part we don't have to break down any further, but now we have something that we can break down further. So we're focusing on this piece, and I listed all the potential rational zeros, and that's important. These are rational. It's not all zeros you can find, but the ones that are the easiest to work with are rational. And now we're going to see which one of these is a 0 of this function. So let's call this function g of x. I'm going to plug in, let's plug in 1. So if I plug 1 into here, I get 1 plus 2 minus 5 minus 10. That's -15 plus 2 plus 1. I just want to see if it equals 0. This does not equal 0, so 1 is not a factor. Let's plug in -1. We get -1 plus 2 plus 5 minus 10. So this gives me -1 plus 2 minus 5, which is not equal to 0. So that doesn't work. Okay, let's try 2. G of 2 is equal to 2 cubed is 8 plus 2 times 4 minus 5 times 2 minus 10. Let's simplify that. That's 8 plus 8 minus 10 minus 10. So that's 16 minus 20, which is -4. That's not 0. So +2 doesn't work. Okay, let's try -2. We're going to plug in -2 into the function. What are we going to get? -2 cubed is -8. Then we have, let me zoom out a little bit. And I also want to put some space here. Okay. All right, and then we have plus 2 times a negative 2 squared, which is 4, minus 5 times a negative 2, minus 10. So you'll see that this is negative 8 plus 8, plus 10 minus 10. These cancel, and we get 0. So negative 2 is a root. Okay, we found one root. And we could try the other ones too, but what I'm going to do now is because I have a root that tells me that x plus 2 is a factor of g of x. Remember, it's x minus c, and then when we plugged this in, that was the c, and when we plugged in c and we got 0, which means we got a remainder of 0, that would make x minus c a factor. So x plus 2 is a factor. So what are we going to do with this? Remember the goal. The goal is to completely factor this function. So we need to break this piece down. So we're going to take this piece and we're going to divide it by x plus 2. So let me make some space. I guess we're going to make it right here. Okay. So let's take this, x cubed plus 2x squared minus 5x minus 10, and let's divide it by x plus 2. So what will we get? We get x squared. Okay, so subtract this, and we get 0, x squared, and bring this down to minus 5x, and bring this down too, because if we get rid of this, because at 0, we need 2 pieces for this to work. So then we have a minus 5. Minus 5 times this gives us minus 5x minus 10, and then we subtract both. So we change the signs and we get 0 as the remainder. So you see that we get x plus 2 times x squared minus 5 would give us this polynomial. So let me write it here. X squared minus 5 times x plus 2. Okay. Let's rewrite this original function right here as 3x times this times this. Is this completely factored? Well, it is completely factored over the rational numbers, but if we want to factor it over the real numbers, we can break this because this is the difference of squares where we're using the square root of 5. So let me write the next piece, which is, I'm going to write it up here. So this is, we found 3x, x cubed plus 2x squared minus 5x minus 10. And then we found that this was equal to 3x times x squared minus 5 times x plus 2. Okay? And then from there, we can factor this as 3x, x minus the square root of 5, x plus the square root of 5, x plus 2. Now, if I use the rational zeros theorem on this polynomial function, it would be factors of 5 over factors of 1, and you would just get plus or minus 5. And neither one of those factor this polynomial. So that rational zeros theorem doesn't give you all the zeros, all the real zeros, as you can see. I just set this equal to 0 and move the 5 to the other side and took the square root. And so you see if you multiply these two together, you'll get x squared minus 5. So now this is completely factored. Okay, I want to do one more problem and then we'll stop here after this problem. So I have f of x is 3x to the 4th plus 4x cubed plus 7x squared plus 8x plus 2. My goal is to completely factor this, well, as much as I can over the real numbers. It's possible we'll get complex roots, and we'll talk about that later, but we're going to factor over the complex numbers. Sorry, over the real numbers. So factor over the real numbers. So in other words, we'll deal with complex roots, if there are any. I'm not saying there are, but complex roots later. So degree 4, which tells us we could have 4 max roots or 4 factors. And then the rational zeros theorem. So rational zeros theorem will give us some candidates for zeros. So we take this number and this number. So we're going to have factors of 2. So we're going to do plus or minus 1 and 2. Factors of 3 are 1 and 3. So all our potential factors are 1 over 1, which is 1. 1 over 3, which is 1/3. 2 over 1, which is 2. And then 2 over 3, which is 2/3. So we have 2, 4, 6, 8 different numbers we can choose from that could possibly be zeros for this function. Now, this is a bunch of trial and error, but I'm going to be picky because I kind of already know how this factors. So I'm going to go with a positive, actually negative 1/3. So let's plug in negative 1/3 as our first candidate. Plug that into the function. You can plug any one you want into this function here to figure out if it could be a 0, but I'm going to go with negative 1/3. So we got 3 times negative 1/3 to the 4th plus 4 times negative 1/3 cubed plus 7 times negative 1/3 squared plus 8 times negative 1/3 plus 2. Now these are ugly. You've got a lot of fractions here. I would plug it into a calculator. But if you do, what's going to happen is you're going to get 0. And that tells us that x plus 1/3 is a factor of f of x. Okay, that's important. So because it's a factor, what we can do is we can take this long polynomial and then divide it by x plus 1/3. Let's do that. So let's get rid of this. Okay. And I'm going to do this here. Okay, so let's put right here x plus 1/3 again. When we plugged in negative 1/3, we got 0. So x plus the opposite of this number is a factor. So I'm going to divide that into 3x to the 4th plus 4x cubed plus 7x squared plus 8x plus 2. Okay, let's just start by seeing what we need to multiply this by to get 3x to the 4th. Well, that's 3x cubed. You multiply that, you get 3x to the 4th. We're going to be careful here. We've got fractions. So you're going to take 1/3 of 3x cubed. Well, the 3's will go away, and you're just going to be left with x cubed. Subtract, and you'll get 3x cubed plus 7x squared. Okay, to get 3x cubed, we have to multiply by 3x squared to this x here. So we'll get 3x cubed, again, 3x squared times this 1/3, it'll cancel out that 3, and you'll get just x squared. So now we subtract, and we'll get 6x squared, pull down the 8x, And to get 6x squared, we need to multiply this by 6x. So we'll get 6x squared, and then 6x times 1/3, well, that will be 2x. Subtract, and then we'll get 6x plus 2, which to get that 6x, we need to multiply by 6. Then we'll get 6x plus 6 times 1/3 is 2. And we should always get 0 as the remainder because we know that it was a factor. So we got 0 here. So this piece times this piece gives us this function. So let's write that here. So this is equal to x plus 1/3 times 3x cubed plus 3x squared plus 6x plus 6. Okay, so we've partially factored this. Now we need to focus on this piece and try to factor that. First off, notice that we have a greatest common factor. Let's pull out the 3. And I'm going to put this in the front. So we've got 3x plus 1/3 times x cubed plus x squared plus 2x plus, this will be 3, sorry, 2. Okay, you have a couple of options here. You can send this 3 into this guy here, and it'll take a form that you're more used to seeing, which is 3x plus 1. Or you can leave it out. It's fine if you leave it out like that. But what I'm saying is you could send it in and make this 3x plus 1. And if you set it equal to 0, you can see that you get the 1/3, like we got here. Okay, now we need to find potential factors of this. So let's move all of this down. Okay, this has a degree of 3, which tells me that it could factor and have at most 3 roots. So let's see all the potential factors. So we take this number 2. The potential factors are factors of 2, which is 1 and 2, divided by factors of the number here, which is 1. So our potential zeros are plus or minus 1 and plus or minus 2. I'm going to go with -1. Let's plug that into this function here. So if we call this function, let's call it g of x. If I plug in -1 into this function, I get -1 because -1 cubed is -1, plus 1 minus 2 plus 2. And you can see that I get 0. I knew that this was going to be a factor. But of course, if you don't know anything about this, you're going to have to just choose some of these factors and see what you get. And then if you don't get the right one, just choose a different one. So if you plug in -1, you get 0, which tells me that x plus 1 is a factor of g. Okay, so then let's try to factor this. So I'm going to insert some space here. I'm going to write this piece here, x cubed plus x squared plus 2x plus 2. And I'm going to divide by, clean that up, x plus 1. Let's see what we get. So we get x squared, subtract, subtract. We'll get 0, so let's carry both of these down, 2x plus 2. So we multiply by 2, subtract, subtract, we get 0, and that's our remainder. So you can see that this piece breaks into x plus 1 times x squared plus 2. So let's write that down. This is equal to 3x plus 1 times x plus 1 times x squared plus 2. That's a 2 right here. Sorry about that. Okay. So is this completely factored? Sorry, it jumped way up there. So let me go back. Sorry about all the screen scrolling here. I think, here we are. Is it completely factored? Well, it is completely factored over the real numbers. It's not completely factored over the complex numbers. In fact, if you put the square root of 2i here, or the negative square root of 2i, then you could factor this a little bit more, because that is a 0. So what we're going to learn in the next video is how to write the complex factors. So for right now, this is as factored as we can get it.